Alright, in this video we're going to show how to solve the following titration problem, which comes out of OpenStax Chemistry 2nd edition. This is 94 in the acid-base chapter. And we want to know, well, if we have 40 mils of this certain concentration of barbituric acid with a Ka that's given, and we're using 0.1 molar potassium hydroxide, what is the pH of the following, the following compositions, right, where there's progressive amounts of the potassium hydroxide that are added. And so for this problem, I think what we really want to do is we want to, first, let's just call barbituric acid HA, right? We've gotten used to this convention where we call the acids, the weak acids, HA, and the conjugate is A minus, and I think that's a good, convention to use for this one where we don't necessarily have the barbituric acid formula readily available. So if this is the case, what reaction is occurring? And I do want to remind you that, if you were able to get partway through this video or just as you're working through for the different questions, just go ahead and feel free to pause the video as you go. Definitely try to put yourself to the test as much as possible. Okay, if we have barbituric acid, HA, and we're adding potassium hydroxide, this is our reaction. We see potassium hydroxide, we think that's hydroxide. It's a group 1 metal, potassium, and that's just going to be inert, and what we're really dealing with is hydroxide. Okay, with that established, which again is the reaction that occurs as we add hydroxide to this problem, we want to think if this is a titration, what is the equivalence volume? So at what point will we have exactly the amount of hydroxide to neutralize this acid HA? And here, this is really stoichiometry, right? We want to say how many moles of barbituric acid do we have? We need 1 mole of hydroxide for every 1 mole of barbituric acid. So how much volume of this specific concentration is needed? And this may look like kind of a long solution, but these really are the steps you should use. In this case, we have the same concentration of the acid and the potassium hydroxide, so it's like the same volume, and it looks kind of simple. But we do want to know that this is a stoichiometry problem. We want to convert to moles of the acid, convert to moles of the hydroxide, then convert to volume of the hydroxide solution, and then we can get it into milliliters. Okay. Once we have these things established, right, we know now the equivalence point. We want to know what exactly are we dealing with for each addition of the potassium hydroxide. And so here, is another good opportunity to pause and see if for A through E, we can briefly describe the composition. In other words, what is there, right? Is there weak acid? Is there weak base? Is it a buffer? Is there excess hydroxide? These are the things we want to watch out for. For A, it's a pure weak acid. We haven't done anything to it yet. All we have is 0.1 molar barbituric acid. For B, note that we're at the half equivalence point, and this means we have a 50-50 mixture of HA and A minus. For C, this is just before the equivalence point, and so we mostly have A minus, but there is still going to be some HA, and we can probably use an approach to solve as if it's a buffer. For D, this is the equivalence point. We know that 100% of the HA has been converted to A minus, and there's no excess hydroxide. Therefore, this is going to be like a weak base problem. And finally, at 41 milliliters, we're going to have A minus and OH minus, A minus and hydroxide, and the stronger base, OH minus, is going to be what determines the pH of this solution. Okay, so let's go through each of these steps. For a pure weak acid, how do we solve for the pH? And I'm going to kind of go through this a little bit briskly. If you want some more review, I definitely recommend checking out some, weak acid review, buffer calculations. These are all really good things to refresh yourself upon because titration really brings all of these topics together when we look at one of these weak acid titrated with a strong base problems. Because here, with no potassium hydroxide added, it's simply a pure weak acid, and we want to start by getting the reaction and the Ka, right? What is the weak acid equilibrium that we're dealing with here? It's the following, right? Weak acid in water is in equilibrium with its conjugate and hydroxide. And the Ka is given. We know that Ka is going to have the following form, and we can set up our ice table, right? We have 0.1 molar barbituric acid. It's going to shift to the right, and it's going to end up with the following, for which, why don't we go ahead and assume that 0.1 minus x is about equal to 0.1. This is based on being a low value of Ka. It's a mathematical approximation that we should see that this x here probably doesn't matter. And we're going to be able to test this as well. Plug in, we end up getting x is equal to 3.13 times 10 to the negative 3. So it does look like it's less than 5% of the 0.10, which is the threshold for making this common acid-base approximation. And we can get the pH from this, 2.5 for the pure weak acid solution. For B, we're at the halfway equivalence point. And you can go ahead and do a reaction table. We'll show how to do that in just a second. But if you're feeling kind of savvy, you know, what we can say is that's at the halfway equivalence point. pH equals pKa. The buffer is 50%, HA and A minus. This means that it's going to be pH equals pKa, and we're done, right? Just get the pKa, that's the pH, that is all you need for this one. Halfway equivalence point means that we have a pH equals to pKa. Okay, what about just before the equivalence point? And here, we do want to make sure that we're taking into account the concentrations of the HA as well as the A minus that's formed. So what is the composition of this buffer when we don't quite get to the equivalence point? And here we want to pull out that reaction that we already stated, right? This is the reaction that occurs. What happens in our reaction table? Well, initially we have the following amounts, right? And this I got from converting from molarity and the volume to moles. We want to always use moles when we're doing a stoichiometry problem, like this one that is an acid-base neutralization. We know that it will proceed to the greatest extent that it can, which is going to be limited by the hydroxide. So we're going to lose that amount on the reactant side, form that amount on the product side, and we end up with the following composition. Note for the water, we don't really know like exactly how many moles of water we started with. I mean, I suppose we could calculate it, but it's not really necessary. Just putting this here to note that we start with lots of water, it does produce water in this reaction, and we end still with lots of water. So with this, we can use our Henderson-Hasselbalch equation, which shows the pH based on the hydroxide, not the hydroxide, but the pH based on the HA and the A minus, the composition of the buffer. And we get the following. This is Henderson-Hasselbalch on the left, and it evaluates to 5.60. Very usefully, we can just use moles of HA and A minus here because they're both in the same volume. So if we considered molarity, that would just cancel out as well. Okay, what about at the equivalence point with only A minus? Here, right, remember that we saw that it was stoichiometrically equivalent. That's how we determine the equivalence volume of 40. And so all the HA has been converted to A minus. So we want to know that if all we have is this conjugate, if we have the barbiturate ion, the A minus, we have the following, right? Is A minus in water makes for equilibrium. And we solve for Kb based on the Ka of the barbituric acid. So this is from Ka times Kb equals Kw. This is to say if we have the Ka of our weak acid, which we do, we can calculate the Kb of our weak base conjugate, which we've done here. And this is the equilibrium and the reaction. Now that we have the equilibrium constant and the reaction of interest, this is pretty much the same as before, except note that we do really need to care about the molarity here because we started with a 0.1 molar solution and we doubled the volume, so the molarity is going to be halved. So really when we have this A minus solution, it's based on a molarity of 0.05 molar. From there, everything really is the same. We get the following. We can make our approximation here. This should really be 0.05 minus x is about equal to 0.05 in the bottom. Sorry about that. But we plug into Kb. We have our unknown, and we solve for x is the concentration of the hydroxide, which is 2.26 times 10 to the negative 6. That gives us our POH, which gets us our pH, and the pH here is 8.35. Last question is beyond the equivalence point, what is our pH? And so this is, we've gotten to the equivalence point, but we've added an extra mil of this KOH solution. And so again, we want to think of our reaction, and we want to think about what do we put in there to combine, right? And it's 0.004 moles of HA and a little bit more hydroxide. Again, it tries to combine to the greatest extent that it can, which leaves us with A minus and this small amount of hydroxide ion. With a stronger base present, that is the one that's going to determine the pH. We can kind of totally ignore the A minus. While it is a bit basic, it's not going to be able to take protons like hydroxide will. And therefore, the pH is going to be dependent on that stronger base. So note also here that we added 41 milliliters of water, and the final volume is going to be 81 milliliters of water. This is important for getting our hydroxide concentration, which I calculate as the following. With this, we have hydroxide, so we're pretty much done. We get our POH, and we get a pH equals 11.09. So that is kind of an involved problem. It ties together a lot from the acid-base chapter, and if you're able to get all these different pHs, I think you're going to be well on your way. And if not, definitely review each of these 5 different subparts of the problem. They're all very relevant, and I think would be great practice for you as you continue to prepare for acids and bases.